Welcome. In the last video, we have discussed the Olkin's bivariate ratio estimator. We have compared with usual ratio estimator with one auxiliary variable and also with simple mean estimator when we do not have any auxiliary information available to us. And we have derived the conditions under which the bivariate ratio estimator is preferable to other two cases. Now, in this video, we shall generalize this bivariate ratio estimator to a multivariate case where information on p auxiliary variables is available to us. So, the multivariate ratio estimator for p auxiliary variables is given by y-mr bar, that is equal to w1 yr1 bar plus w2 yr2 bar plus up to so on plus wp yrp bar, where summation I equal to 1 to p wi equal to 1 and yrI bar equal to y bar into xi bar by xi bar, I equal to 1 to p. Now consider yrI bar minus y bar, that is equal to y bar into xi bar by xi bar minus y bar. Now this is equal to xi bar by xi bar, this will be y bar minus y bar by xi bar into xi bar. Now this will be equal to xi bar by xi bar into y bar minus ri xi bar, where ri equal to y bar by xi bar. This is the population ratio for the ith study variable with ith auxiliary variable. Now for large samples, we have xi bar by xi bar, this is approximately equal to 1. So for large samples, expectation of y ri bar minus y bar, this is equal to 0. So this shows that if the sample size is large, then the ratio estimator yrI bar based upon the ith auxiliary variable is an unbiased estimator of the population mean y bar. So for large samples, we can write expectation of y-mr bar, that is equal to summation I equal to 1 to p wi expectation of yrI bar, that is equal to y bar. So that is y-mr bar. This gives an unbiased estimator of the y bar when the sample size n is large. Now we have to find the large sample variance of the multivariate ratio estimator y-mr bar. Now variance of y-mr bar, that is the variance of the multivariate ratio estimator, equal to variance of summation I equal to 1 to p wi yrI bar, that is equal to summation I equal to 1 to p wi square variance of yrI bar plus I not equal to j varying from 1 to p wi wj covariance of YRI bar and YRJ bar. Now that is equal to summation I equal to 1 to P Wi square VII plus summation I not equal to j varying from 1 to P Wi Wj Vij, where VII equal to variance of the ith ratio estimator with ith auxiliary variable. So that is equal to 1 minus f by n y bar square c0 square plus ci square minus 2 rho 0 I c0 c I equal to 1 to. Now Vij, this is equal to covariance between the ratio estimator based upon the ith auxiliary variable and jth auxiliary variable. This is also equal to 1 minus f by n y bar square. This is c0 square minus c0i minus c0j minus rho ij ci cj. This is plus. Now we shall proceed further by defining the matrices, different matrices as follows. We define the matrix, a P cross 1 matrix, that is the matrix of the weights W1, W2, WP, and P cross P matrix VP cross P, this consisting the variances and covariances V11, V12 up to V1P, V21, V22 up to V2P, then VP1, VP2 up to VP. And we define E. This is a P cross 1 matrix. Elements are each 1. So variance of the multivariate ratio estimator can be written as summation, this is I equal to 1 to P Wi square VII plus I not equal to j varying from 1 to P Wi Wj Vij, that is equal to W dash Vw. Now to determine the weights Wi, we now minimize this variance subject to the condition E dash W equal to 1. That is summation I equal to 1 to P Wi equal to 1. So now let us define a function I that is equal to W dash Vw plus mu E dash W minus 1, where mu is the unknown Lagrange's multiplier whose values are to be determined. Now differentiating I with respect to W and equating to 0. Now del phi by del W equal to 0 implies W dash V plus mu E dash equal to 0. That implies W dash V equal to minus mu E dash. That implies W dash V inverse equal to minus mu E dash V inverse, post multiplying V inverse both sides. That implies W dash into I equal to minus mu E dash V inverse. That implies W dash into I is the identity matrix. So W dash equal to minus mu E dash V inverse. Now taking transpose in both sides, W dash again transpose, that is equal to minus mu E dash V inverse transpose, that is equal to minus mu V inverse E. So that implies W equal to minus mu V inverse E. Now this is equation 1. Since E dash W equal to 1. So now from this we get E dash W pre-multiplying E dash, that is equal to minus mu E dash V inverse E, that is E dash W equal to 1. So this is 1 equal to minus mu E dash V inverse E, that is equal to minus mu equal to E dash W by E dash V inverse E, that is equal to 1 by E dash V inverse E. Now we consider E dash V inverse E. Consider E dash V inverse E, that is equal to E dash 1 1. E is the elements 1 P plus 1 matrix, so E dash row matrix, each element 1. So this is V11, V12, V1P, V21, V22, V2P, similarly VP1, VP2, VP. This inverse 1. Now this is equal to 1 1. This is V11, V12, V1P, V21, V22, V2P, similarly VP1, VP2 up to so on VPP into 1 1 1 like this. Where Vij is the ijth element of V inverse. Now this is equal to V11 plus V21 plus up to plus VP1 then V12 plus V22 plus up to plus P2. Now up to so on, the last element will be V1P plus V2P plus up to plus VP. Then column matrix 1. Now this will be equal to sigma 1, sigma 2, sigma P, then 1, 1, up to so on, where sigma I is the sum of P elements of the ith column of V inverse. Now this will be equal to this will be sigma 1 plus sigma 2 plus up to sigma P, that is equal to sigma, that is equal to sum of all the P square elements of V inverse. Now putting the value of mu minus mu in equation 1 previously, we get the W cap equal to V inverse E divided by E dash V inverse E, that is equal to sigma 1, sigma 2, sigma P transpose divided by sigma, that is equal to sigma 1 by sigma, sigma 2 by sigma, sigma P by sigma. Yes. Now we have obtained this. Now let it be equal to W1 cap, W2 cap, WP cap. Yes. Where Wi cap equal to sigma I by sigma I equal to 1 to P. Now using this we can get the variance of the multivariate ratio estimator in its minimum case. Now we can use this W cap. This is equal to W dash BW, that is equal to E dash V inverse by E dash V inverse E into V. This will be V inverse E by E dash V inverse E. So that is equal to E dash V inverse E divided by E dash V inverse E into again E dash V inverse E. That is equal to 1 by E dash V inverse E, that is equal to 1 by sigma. So minimum variance of the multivariate ratio estimator YMR bar is 1 by sigma. If you take P equal to 2 for any particular case, then we can get V equal to B11, B12, B21, B22, and then V inverse will be equal to V22 by delta V minus V21 by delta minus V V12 by delta, V11 by delta, where delta equal to V11 V22 minus V12 square. So we get W1 equal to sigma 1 by sigma, that is equal to V22 minus V12 by delta divided by V11 plus V22 minus 2 V12 divided by delta. So that is equal to V22 minus V12 by V11 plus V22 minus 2 V12. Similarly, we can get W2 equal to sigma 2 by sigma, that is equal to V11 minus V12 by V11 plus V22 minus 2 V12, which is the bivariate ratio estimator. Now, we have to compare the variances. Comparison of variances. Now, here we shall compare between the ratio estimator using P auxiliary variable YMR bar with that of the ratio estimator using Q auxiliary variable, where Q less than P. That means here we take less number of auxiliary variables than here. Now second comparison we shall make the ratio estimator using P auxiliary variable with that of the simple mean estimator Y bar under simple random sampling without replacement scheme. So now let us compare the two multivariate ratio estimators, one using lesser number of auxiliary variables. That means comparison between YMR bar using P auxiliary variable and YMR bar using Q auxiliary variables, and here the Q less than. Now for this we take the Olkin's assumptions. The first, our study variable Y is equally correlated with all the auxiliary variables. So that is rho 01 equal to rho 02 up to so on, that is equal to rho 0p, that is equal to rho 0. Second, rho ij equal to rho for all I not equal to j varying from 1 to p. That is, the correlation between any two auxiliary variables is same. Now the third assumption, the coefficient of variation of all the auxiliary variables are same. That is, C1 equal to C2 equal to C3 equal to Cp equal to C. So under these assumptions, VII equal to variance of YRI bar, that is equal to 1 minus F by N into Y bar square C0 square plus C square minus 2 rho 0 C0 C, that is equal to R say or I equal to 1 to. Now Vij, that is equal to covariance between y bar ri and y bar rj, that is equal to 1 minus f by n y bar square. This is c0 square minus 2 rho 0 c0 c plus rho c square, that is equal to say lambda. So the v equal to r lambda all lambda. So this is lambda r lambda, so on lambda lambda r means all the diagonal elements are that is the variance of the ith auxiliary variable, and off diagonal elements are lambda. So let V inverse, suppose V inverse is theta mu, then mu, theta mu, then mu, mu, theta. Diagonal elements are theta, all other elements are mu. This is P cross P. This is also P cross P matrix. Now here theta equal to cofactor of R divided by determinant of V. So theta equal to here R lambda 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 R lambda, then lambda lambda R divided by this is P minus 1 cross P minus 1 matrix divided by R lambda lambda, then lambda R lambda, then lambda lambda R. This is P cross P matrix. So now consider this denominator P cross P matrix R lambda 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 R lambda 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 R. This is P cross P matrix. Now this is equal to, now we replace first row by row 1 plus row 2 plus row 3 plus up to row P. So sorry, replace first column C1 by C1 plus C2 plus up to CP. Now this will be equal to R plus P minus 1 into lambda, then R plus P minus 1 into lambda, up to so on, last also R plus P minus 1 into lambda, then lambda lambda R, then lambda, then last column lambda, it will be R. So this will be equal to R plus P minus 1 lambda, taking common we have 1 1 1, then lambda, then R, all other elements are lambda, then lambda. Now we now we multiply first column by lambda plus 1 and subtracting it from the other columns. We get r plus p minus 1 lambda, then we get 1, 1, 1 first column, this will be 0, this will be r minus lambda, 0, then all these will be 0, this will be r minus lambda, this will be p plus p. Now this will be r plus p minus 1 lambda into r minus lambda to the power p minus 1. Similarly, the numerator r lambda 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 r lambda, then lambda lambda r. This is p minus 1 into p minus 1 matrix. So this will be r plus p minus 1 into lambda into r minus lambda to the power p minus 2. So we get theta equal to r minus lambda to the power p minus 2 into r plus p minus 2 into lambda divided by r minus lambda to the power p minus 1 r plus p minus 1 into lambda. So this will be now equal to r plus p minus 2 into lambda divided by r minus lambda r plus p minus 1 into lambda. Now mu equal to, then mu equal to, we have cofactors of lambda divided by determinant of v. So that will be equal to minus 1 to the power 1 plus 2. This will be lambda, lambda, all lambda, then lambda r, lambda, 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 then last will be lambda, lambda, r. This will be p minus 1 plus p minus 1 matrix. This divided by determinant of p. Now this is equal to minus 1 to the power 1 plus 2. So this will be lambda 0, lambda r minus, subtracting lambda from every column, r minus lambda. So this is 0, then lambda 0, this is r minus lambda. This is p minus 1 cross p minus 1. this divided by determinant of. So this will be equal to minus 1 to the power 1 plus 2 lambda into r minus lambda to the power p minus 2 divided by determinant of b. So this is equal to minus lambda r minus lambda to the power p minus 2 divided by r minus lambda to the power p minus 1 r plus p minus 1 lambda. So now the value of mu becomes equal to minus lambda divided by r minus 2. Sorry, this is equal to r minus lambda r plus this is p minus 1. So the minimum variance will be equal to 1 by sigma, that is equal to 1 by this is sum of p square elements of v inverse, that is equal to 1 by p theta plus p into p minus 1. So using values of theta and mu, we get minimum variance of the multivariate ratio estimator using p auxiliary variable, that will be equal to 1 divided by p into theta. In place of theta we shall put r plus p minus 2 lambda divided by r minus lambda into r plus p minus 1 lambda plus p into p minus 1, we have minus lambda divided by r minus lambda into r plus p minus 1 into lambda. So this is equal to 1 divided by this will be pr plus p square lambda minus 2p lambda minus p square lambda plus p lambda divided by r minus lambda into r plus p minus 1 into lambda. So this will be equal to p square lambda cancels out, minus 2 p lambda plus p lambda, this will be p lambda. So p taking common, this is r minus lambda. So we have r plus p minus 1 into lambda by p. This is equal to 1 by p, r we have equal to VII plus p minus 1 VIJ. So minimum variance of the multivariate ratio estimator with P auxiliary variable, that will be equal to 1 by P using values of VII and VIJ. This will be 1 minus F by N y bar square. This will be C0 square plus C square minus 2 rho 0 C0 C plus P minus 1 into 1 minus F by N y bar square into C0 square minus 2 rho 0 C0 C plus rho C square. So this will be equal to, this is on simplification, we can take 1 minus F by N y bar square common, then this will be y0 square by P. Then we have C0 square plus C square minus 2 rho 0 C0 C plus P minus 1 C0 square minus 2 P minus 1 rho 0 C0 C plus P minus 1 rho C square. Now this will be equal to 1 minus F by N y bar square by P. This is P C0 square plus 1 plus P minus 1 rho C square minus 2P rho 0 C0 C. So this will be equal to 1 minus F by N y bar square by P to P C0 square plus 1 plus P minus 1 rho this will be y bar square 1 by P will multiply C0 square plus 1 plus P minus 1 into rho by P into C square plus 2 rho 0 C0 C. So this is the minimum variance using P auxiliary variables. So for P equal to 2, we can also we can use P equal to 2 here. We can get the, it will be reduced to the bivariate ratio estimator. So for P equal to 2, we can get the minimum variance for the bivariate ratio estimator as 1 minus F by N y bar square C0 square plus C square by 2 1 plus rho minus 2 rho 0 C0 C. Now similarly, we replacing P by Q, variance of minimum variance y bar bivariate ratio estimator with multivariate ratio estimator with Q auxiliary variables. That will be equal to 1 minus F by N y bar square. This will be C0 square plus 1 plus Q minus 1 into rho divided by q c square minus 2 rho 0 c 0 c. So now we subtract minimum variance with multivariate ratio estimator q auxiliary variable minus minimum variance of multivariate ratio estimator using p auxiliary variable q less than p. That will be equal to 1 minus f by n y bar square c square one plus q minus 1 into rho by q minus 1 plus p minus 1 into rho by p. Now that is equal to 1 minus f by n y bar square c square. This will be p minus q into 1 minus rho divided by pq. So this will be equal to 1 minus f by n y bar square c square 1 by q minus 1 by p into 1 minus rho. This is greater than equal to 0. That implies the minimum variance of the multivariate ratio estimator using q auxiliary variable is always greater than equal to the minimum variance of the multivariate ratio estimator with p auxiliary variables, where q less than p. So it follows that the multivariate ratio estimator using p auxiliary variable is unconditionally superior to that using q auxiliary variable where q less than p. That is, more the number of auxiliary variable used, more will be the efficiency of the multivariate ratio estimator. Now, again, we compare it with the simple mean per unit estimator. Variance of y bar, we have minus variance of multivariate ratio estimator using p auxiliary variable. So that will be one minus f by n y bar square. This will be 2 rho 0 c 0 c minus c square by p 1 plus p minus 1 into rho. So the multivariate ratio estimator, this will be superior to the simple mean estimator if this is greater than equal to 0. So that implies this term is positive, means 2 rho 0 c 0 c is greater than equal to c square by p 1 plus p minus 1 into rho. So that implies rho 0 greater than equal to c by c0 1 plus p minus 1 into rho by 2. So therefore, if the above condition, this condition is satisfied, then only multivariate ratio estimator using p auxiliary variable is superior to the estimator using no auxiliary variable, that is the simple mean estimator under SRS WR scheme. Thank you.